Hello everyone, my name is Arash Kadrani and today I'd like to talk about fast sampling SAR ADC. Here you can see an architecture of a SAR ADC. It has a track and hold which sample the analog data. Then this comparator compare it with a reference. If the sample data is less than the reference, the most significant bit will be 0. Here you can see that. Then through the logic and the DAC reduce the reference to half of the previous reference and do the comparing. Here will be 1 and the most significant bit will be 1 and so on. Regarding the speed, you need 1 clock for each bit, and 1 clock for the sampling. So the clock frequency is n plus 1 time of the sampling frequency. Also regarding the frequency and clocking, because DAC has a settling time, comparator has a delay and logic also has a delay, you should consider the sum of all of these to define your main clock. And the main clock period should be more than this because this part of the ADC needs to settle and do the conversion and the decision. Regarding of the bandwidth, there are two main problems. One is the capacitive loading of the track and hold on the TIA, and also the ADC on the track and hold. The track, for example, the track and hold of the capacitive loading of the track and hold can limit the frequency behavior of the TIA, which is very critical part of this kind of a design if you use the TIA or another front-end. Here you can see that I modeled the track and hold with R-on and CS. Beside the loading problem, there are inherent problem of the bandwidth for the track and hold. For example, R-on and CS should be small to have a smaller time constant. If you reduce the CS or sampling capacitor, you increase the noise on it because of this equation. If you decrease the R-on, for that you should do two things: increasing the ratio or the sizing of the transistor, or increasing the gate source. If you increase the gate source, you would have the limitation of the VDD and some other problem. If you increase the sizing, clock fit through charge injection, and higher capacitive load on the TIA would bother you. So there are two main problems: loadings and bandwidth limitation of the track and hold. In literature, you see two approaches to remove this limitation. One of them, or one category, is systematic solution, and the other one is circuit design solutions. Regarding the systematic approaches, time interleaved SAR ADCs play a very huge role. Here you can see, instead of using a one sampling, they use n sampling in parallel. So they are sampling at n fs, which fs is the sampling frequency of one of these. While the bandwidth of these ones are still fs divided by n. So as you see in the timeline here, so each time the main clock tell one of this to take a sample, and by this you increase the sampling rate, while you do not need to increase the frequency behavior, like to make the frequency behavior of track and hold better. In this configuration also you can see that you have more hold time for the ADC to make the conversion and to do the digitization. The problem with this configuration is because you have a main clock which tell each of them to turn on and off, you might have time misalignment between these clocks, and you have too many critical clocks, and routing them and conveying them from the main clock to each of these sample and holds wouldn't be easy. The solution is to use the front-end switching. So this one still sample at this high frequency, but instead of the main clock, the front-end switch tell each of them to be on. So the matter of misalignment would time misalignment would be less critical. The problem with this configuration is that the front-end switch always see the parasitic of these switches, which kind of limit its frequency response and behavior. To remove this, you can use inline demask sampling. So there's some sample switches, or let's say there is some switches in between the front end and the sample switches. So in this case, instead of having the parasitic loading of all of these sampling switches, you only have the parasitic loading of these switches in between. One good thing about this configuration, as you can see here, is so when this one is on, this one will be on, and then this one will be on. When they are going to turn off, so this turn off, and then this turn off. This kind of make no charge injection from this switch on the sampling switch, on the sampling capacitor, because, for example, SP1 is off. The disadvantages, you have the sum of all of these resistive passes on the frequency behavior. To remove a loading problem between the ADC and track and hold and the front end, they mainly use voltage buffers. For example, here you see an example that a voltage buffer has been used between the front end and the sampling capacitor, and here between the ADC, for example, and the track and hold. So the capacitor of the sampling wouldn't load the front end, and the capacitor of the ADC, which is nonlinear, wouldn't load the switch and wouldn't load the sampling. The gain of a source follower used as a voltage buffer could be defined by this equation. Here, in this equation, you see the gain is not 1, so it's not ideal, and also the gain is nonlinear, which means if you have variation in the input and the output, so RO is changing, GM is changing, so you have nonlinear effect. Remember, because of the fast speed matters, you mostly use a transistor with very small lengths, which they are more sensitive to channel length modulation. Here also I mentioned that gate source, for example, in this configuration, in this circuit, because the gain from here and here is positive and almost 1, the gain source effect on the sampling switch is very limited due to the Miller effect. To remove the nonlinearity, you can use an op amp in feedback. We know feedback make everything more linear, and the gain now wouldn't be defined by the transconductance of transistor or their output resistance, which both are nonlinear. And the gain will be defined by a ratio of this resistor. Remember that ratio of a resistor in nowadays technology is very robust, and it wouldn't change with a variation in temperature and process. However, it comes with the cost of lower bandwidth, because you should design a high gain system, high gain op amp, to remove the nonlinear effect of the op amp on the feedback gain. It has complexity and also power consumption, all because of the using of the op amp. There is another example from 90 which has been repeated in this paper and thesis. They call it, if I remember, they call it cascade source follower. So in this case, they limited drain source variation, which caused channel length modulation by using this transistor. So when this goes up through this transistor, these parts go up, and the drain source of the main transistor follow each other. Problem with this configuration is you have more input capacitor limit your speed because of this transistor. Also, the body effect is could be a problem, because you can use deep annual technology or PMOS if you have that in your PDK. Also, another problem that I forgot to mention is that because of the gate source of this transistor, this part and might be in maybe the gate source of this transistor might push this one into triode. It has been suggested in papers to use a low threshold transistor for here if you have it in your PDK. Another way to reduce the drain source effect is to use this circuit. In this circuit, there is a plus. Besides the drain source following each other phenomena, you have also a limited swing for the drain source. Here V in, you can see V in and V out, and V out through this path come back here by, for example, a gain less than 1, because it's a source follower. Here gain is, for example, 0.9, and this is a portion of V out, and as you can see, the drain source swing is limited, so channel length modulation is hugely suppressed. If we consider beta as 0.9 and use this equation, we can find out the second harmonic reduce minus 40 dB and third harmonic minus 60 dB compared to conventional source follower. Also, the gate drain effect of this transistor wouldn't be limiting, and also would be reduced compared to conventional source follower, because the gain from V in and this part is positive, and the Miller effect help us to have less effect of the gate drain here. You might see that this one might have a negative gain from this part to this part, but is not correct because the source degeneration exists here. But maybe in high frequency, the capacitive loading of here bypass this huge source degeneration. There are other examples of source followers. For example, super source follower has been introduced in papers. We know ideal voltage buffer is equal to a voltage buffer with zero output resistance. So if you add the voltage source here, if the voltage source go up, through this common gate, these parts go up, and through this common source, this part goes down. As you can see, the feedback kind of suppress the variation of voltage, and we know because of the Ohm law, this means low resistance or zero resistance. Also in this paper in 2023, from the team that I know, they use another auxiliary pass from here and made it class AB. Another way to make a source valuable ideal is to remove the effect of gate source or the transconductance effect of the M1, for example, here. So when Bin is going on in a conventional one, because of the when Bin goes up, it generates a current, so the GM will change and the out is not exactly following the V in. To remove this effect when V in goes on, so I1 will be introduced and produced. It will copy through this pass. And because the sum of the AC sum of these currents will be zero because the AC current of this part is zero, the M5, which is a current source. So we can say that I1 is zero, so gate source variation is zero. Another one that I like too much is this configuration, this circuit. It is differential, so it has a better PSRR and CMR. Another good thing about this, besides it's very simple to implement, is it's self-biased. Another example is to have a buffer using a differential pair. Here you see M1 and M3 are differential pair, and this is the current tail. In a differential pair in common mode, V in and V out follow each other, and the gate source of these two should always stay equal. To make this happen, for example, when there is variation in the input, so this variation through this feedback will be conveyed to here. If this goes down, it generates the current, and so the current from here bring the out down. So always the gate source stay equal. In a paper in 2006, they explained how to make the feedback even more effective by introducing a positive feedback to increase the impedance in the node number 2. Also, you can remove the effect of or make the buffer more ideal by removing the effect of the ADC on the buffer using a switch, which you can call it a buffer switch. Here in this thesis and the related paper, they explained how with a buffer you have a better settling time. However, without a buffer here, by buffer I mean a switch buffer, you have a very bad settling time in your system. As I mentioned, track and hold also have their inherent problems. I told you that R on will be defined by ratio and gate source. If you increase ratio, you would have loading problem, clock feed through, and charge injection. So one case is to increase gate source. If you increase gate source, you would be limited to VDD. So one way is to use bootstrapping. In this case, you charge a capacitor to VDD, remove the turn off the switches and put the VDD on this part. So you always have a very huge gate source on your transistors. I should mention that implementing this kind of a technique is not easy. However, the idea seems very easy. In books and also in papers, you can follow how to implement this switching without causing any extra effect on the sampling. Also, you can use cascaded based instead of switch based and you kind of integrate the buffering with switching. Here you can see a source follower that I mentioned before compared to a cascade switching with a PMOS loading triode. If you do the equation, you see in this case the main pole at the output is more closer to FT, which FT is a reference related to the technology. P1 is closer compared to this configuration. Here also they show in this thesis very correctly that if you want to have a more high frequency pole in this circuit, which is a conventional source follower, you should increase the power consumption. You can use this kind of a switch in differential. You can make so if you remember in time interval lived, we had switches. They were doing the sampling in different time, so you can implement an of this because they are differential, they are more linear. I have a video about linearity in differential, so they wouldn't have second harmonic. Also, the common mode rejection and supply noise rejection are a plus. So to make them also more linear, instead of PMOS, you can use an NMOS. So you can use the NMOS, which in NMOS, so the nonlinearity of M1 will be removed by M5. You can see it in this equation. The problem is in high frequency, maybe the capacitor loading of here would have a lower impedance compared to 1 over GM5, and you would have some variation here. You can see they kind of simulated this, and they noticed that it's kind of a generate nonlinearity, and this third harmonic increase. Remember, you wouldn't have a second harmonic because it's differential, and then decrease because in very high frequency. So you have coupling between input and output, so and less nonlinear behavior of the transistors. Back to concept of charge injection and clock feed through compared to circuit, one with PMOS load and one with NMOS load. Here you can see when you come from the zero, which this one is in triode, to off. So because it's in triode, the charge will be kind of a distributed. They find more of them goes to the path that has less impedance, for example, maybe this part, and some to here, and some will be recombined with the holes. The good thing here is because M2 is in saturation, so you wouldn't have any charge here that goes here and cause some sort of offset and nonlinearity on the sample that you took. Another good thing about this configuration is the clock fit through kind of will be limited, because when this part goes up, this part goes down, so they cancel out each other. However, in NMOS, because both are in the same phase, which is a kind of a plus for using NMOS, so you can use the same phase clocking, but when they turn off, both turn off in the same phase, so their clock fit through wouldn't cancel each out. Also, you can see some stuff about uh, the charge injection, and why charge injection maybe is more here, because M3 is NMOS in saturation. Also, there is another matter which is mostly about the hold time. So in the hold time, maybe the signal add to your sample because of coupling, parasitic coupling. So you can add dummies, and because it's differential in two phase, so when this one goes there, the opposite one in the opposite phase come here and remove the effect. Same as for here. The problem is if you add this and you want to have a very high speed switching, so this one add parasitic to your output in your tracking time. To remove this, you can remove the effect of the coupling. By coupling, I mean the coupling between drain and source, by using a more related layout for high speeds, and kind of remove the coupling between source and drain. However, you might have DRC problem, or because you have less contact. For example, here and here you have more poly resistance, and that might cause some effect. So you should consider all of this. Here at the end, I'd like to talk about the clock generation very shortly. So in clock generation, and if you remember the time interleaved, so you need different clock with different phases. So you have a main clock, for example, clock number 4, and you can choose it from different phases. If you pause the video, you can see how it is works. So you just select different phases of the one clock. Here also, because of matter of skew and overlapping of the clocks, they added this skew adjustment system here. So they turn on and off all of the switches to increase the skew or decrease it. One good thing that I like to mention here is they put the switch at the top. The reason is when the switches are off, they have less capacitor coupling to the output, and they would less limit the high frequency specification of the system. However, if we do the switching at the bottom, always this capacitor will exist there. Also, they introduced this system in the literature in this paper for changing duty cycle. If we pause the video, the idea is very simple. The one thing is, which is very more related to IC designers, maybe, is this idea here that they kind of compensate for the discharge of this node